Okay, so this is the end of Chapter 11 on solutions. This lesson will cover Chapter 11 sections 11.5 through 11.8. We're going to talk about boiling point elevation, freezing point depression, including the Van Hoff factor, osmotic pressure and reverse osmosis, and colloids. So let's get started. Boiling point elevation, freezing point depression, including Van Hoff factor, and osmotic pressure are all classified as colligative properties. So, if these are all colligative properties, how can we define a colligative property? Well, it's a property that depends on the concentration of a solution. Not on what's being dissolved. So it just depends on basically the number of pieces in the solution. The more concentrated the solution, the greater the boiling point. The more concentrated the solution, the lower the freezing point. The action of a non-volatile solute on a solvent can have four effects. So if I add, so the four effects, I'm just going to list them over here. Okay. Four effects that a non-volatile solute can have on the solvent is lower vapor pressure, lower freezing point, higher boiling point, and lower osmotic pressure. Okay. So let's look at the equation that we're going to be using. We're either going to be using delta T equals I KFM or delta T equals I KBM. Well, obviously, delta T is change in temp. Your I is your Van Hoff factor. And basically, this has to do with the ionization factor. It's sometimes called that, which actually breaks down to the number of pieces. So again, if I had something like NaCl, when that dissociates into water, it forms two ions. So the Van Hoff factor would be I. If I have MgCl2, that dissociates into 1Mg2Cl, so my Van Hoff factor would be 3. Please remember, all covalent compounds do not dissociate and therefore have a Van Hoff factor equal to 1. Okay, that's important. Kf is our freezing point constant, or freezing point depression constant. freezing point and this is going to depend on the substance that you're dealing with, and the KB is the boiling point. Elevation constant. And M is molality, which we already learned was basically moles over kilograms. Okay. Here's a chart that shows you an example of some of the constants. So for water, we know the boiling point's 100 degrees. The boiling point constant is 0.51. Notice the unit, it's kilograms per mole. Freezing point is 0. The constant is 1.86 kilograms per mole. And here's some different compounds that you might need in solving some of the homework problems. Now, on a test, they technically can expect you to know the 0.51 and the 1.86. If it's another substance, they would have to supply it in the test question. So, let's just review a little bit of what we said. Since colligative properties only depend on the number of molecules, ionic compounds have a bigger effect because when they dissolve, they dissociate, unlike covalent compounds which don't dissociate when they dissolve. So as I said, individual Na and Cl ions fall apart. So 1 mole of NaCl makes 2 moles of ions. 1 mole of AlNO33 makes 4 moles of ions. Electrolytes have a bigger impact on the melting and freezing points per mole because they make more pieces. The relationship is expressed using the Van Hoff factor, or I. So your moles of particles in solution over your moles of solute dissolved. From that, we can determine an expected formula. The actual value, as you're going to see, is less because at any given instant, some of the ions in solution will be paired. Ion pairing increases with concentration. So then their I would decrease in concentration. We can change our formulas to reflect delta H equals IKM. So let's look at a few problems. These are probably the easiest problems to solve in this unit. 15.3 grams of sodium chloride, so we know that we're dealing with NaCl, is dissolved in 20 grams of water. What is the boiling point and freezing point of this solution? Well, so we're going to be using delta T equals I KBM, and we're also going to be using delta T equals IKFM. So in order to use this, we need to know the Van Hoff factor. Well, we said it was NaCl, so therefore your I is equal to 2. The Kb and Kf we just saw on the chart. So the only other thing that we need is molality. We need molality in order to proceed. So we have 15.3 grams, and that is per 20 grams of water. And this is the NaCl. So the first thing that I need to do is get moles. So we know that 1 mole of NaCl has a GFM of 58.5 grams. So my grams are going to cancel. That's going to give me moles of NaCl. And we know that molality is moles over kilograms. So we have 20 grams of water and we know that 1 kilogram is equal to 1,000 grams. So grams cancel, and I'm left with moles over kilograms, which is what I needed. So 15.3 times 1,000 divided by 20 times 58.5 is going to equal 13.1 molal. So let's go over here. Let me change colors. Delta T equals 2 times the boiling point constant is 0.51 for water. Our molality is 13.1. So that's going to give us a delta T equal to 13.4 degrees Celsius. Okay, so if water boils at 100 degrees, then 100 plus 13.4, my new boiling point is 113.4 degrees Celsius. That equals my boiling point. And for the freezing point, delta T equals, the 2 is going to be the same. The Kf constant for freezing point is 1.86. Our molality is the same. So delta T is going to equal to also this equals, 49.8. 2 times 1.86 times 13.1 is 49.8. So if water freezes at 100, if water freezes at 0 degrees Celsius, this is going to depress it. So the freezing point would be equal to negative 49.8 degrees Celsius. Okay, next problem. A solution is prepared by dissolving 18 grams of glucose in 150 grams of water. The resulting solution was found to have a boiling point of 100.34. Calculate the molar mass of the glucose. Glucose is a molecular solid that is present as individual molecules in solution. This last sentence is giving you a hint that it's covalently bonded, therefore the Van Hoff factor would be equal to 1. So, looking at our formula, delta T equals I KB M for molality. What do we need to know? Well, we know that our Van Hoff factor is 1. We know that the KB is 0.51. We technically don't know molality, and we know that our change in temperature, the normal boiling point is 100 degrees, so this went up to 100.34, so our delta T is 0.34 degrees Celsius. So if we divide both sides by 0.51, these cancel, and we get molality equal to 0.667. Alright, so we have 0.667 moles per 1 kilogram, because that is the definition of molality, and moles per kilogram. And we know in this case that we have 150 grams of water. So this would be 0.15 kilograms, because we need to get this in moles per kilogram. So 0.667 times 0.15 kilograms is going to be equal to 0.1 moles. So that's part of our answer. We have 0.1 moles. We know that moles equals given mass divided by gram formula mass. We know that we have 0.1 moles. We also know that we're dealing with 18 grams, and we don't know the GFM. So we've got 18 equals 0.1x. Therefore, x is equal to 180 grams. Okay. Osmotic pressure. Well, you should all recall what osmosis is from living environment. It's the flow of something through a semipermeable membrane. In cases of chemistry, it's the flow of a solvent through a semipermeable membrane. Osmotic pressure is the, I guess you would say it's the, if you have a semi-permeable membrane, your liquid levels are different. So I guess liquid levels on either side of the membrane are different. And what happens is there is a greater hydrostatic pressure on the solution than the pure solvent. So this greater hydrostatic pressure is basically the osmotic pressure. Allows solvent molecules to flow, but prohibits solute molecules. Okay. The equation that we're going to use is this symbol that looks like a pi. This is really osmotic pressure. Osmotic pressure is equal to I, again, which is our Van Hoff factor, if we need one, our molarity. So this M is molarity, not molar mass, times R, which is our gas law constant, which is 0.0821, liters per mole dot I think 0.821 liters per atmosphere mole dot Kelvin. And temp in T's temp in Kelvin. Okay. Let's talk a little bit about what's going on before we start with a problem. Here you have two pictures. On the left here, you have the normal flow of a solvent into the solution. So here's your solvent, okay, and it's going to flow into the solution this way across the semipermeable membrane. Now, this flow can be prevented by applying an external pressure up here on the solution. So if I apply an external pressure on the solution, then I can stop this flow. The minimum pressure required to stop the osmosis of this pure solvent into the solution is equal to the osmotic pressure of the solution. Over here on the right, in A, we have a pure solvent and its solution containing a non-volatile solute, and you have them being separated by the semi-permeable membrane in the middle here. You can see that the solvent molecules can pass into the solution, and they can go back across to the left. However, the solute molecules, which are the greenish ones here, can't. In B, we show a system at equilibrium. When the rate of the solvent transfer is the same in both directions. So here they're just basically showing 2 going to the right, 2 going to the left. So the number, or the amount of rate of pure solvent going from left to right and right to the left, is at equilibrium. When equilibrium occurs, the osmotic pressure is this difference here. Okay, let's look at an example. 1 times 10 to the minus third grams of a protein is dissolved into enough water to make a 1 milliliter solution. The osmotic pressure of this solution was found to be 1.12 torr at 25 degrees Celsius. Calculate the molar mass. Well, first of all, you have to know that proteins are basically made up of amino acids, and amino acids are all basically organic. Therefore, if you're looking at your formula, we know that the osmotic pressure is equal to 1.12 torr. Now, because your R is 0.0821, and this unit has atmospheres in it, you know that this pressure has to be in atmosphere. So this has got to be divided by 760 in order to get pressure in atmospheres. So that's the first thing that we want to do, 1.47 times 10 to the minus third ATM. Our temperature is going to be 25 plus 273, so 298 Kelvin. And we said that I was 1 because it's a protein. So if I'm solving for m is going to be equal to pi divided by IRT, which we really don't have to put the I. So m is 1.47 times 10 to the minus third ATMs divided by 0.0821 and 298 Kelvin. And this has got grams per mole, liters ATM, or something like that. And everything's going to cancel. We're going to be left with a molar mass equal to grams is not in here. Kelvin, sorry. Six times 10 to the minus 5 moles per liter. So we're not done yet because we need the molar mass. And there's a crucial piece of information in here. They said that 1 times 10 to the third grams of a protein is dissolved in enough water to make 1 milliliter. So if we have 1 times 10 to the minus 3 grams per milliliter, and we need this to have agreement of units here, we know that 1,000 milliliters is 1 liter. So this same 1 times 10 to the minus 3 grams per milliliter would be 1 gram per liter. Going back to our problem, we can set up a proportion. If 1 gram produces 6 times 10 to the minus 5 moles then per liter, then X grams are in 1 mole, because we know that 1 mole is equal to the GFM, and we're looking for the gram formula mass. So if I cross multiply and divide here, I get 1.66 times 10 to the 4th grams, or basically 16,600 grams. And you might say that that's a very large molar mass, but proteins are extremely large, so that's possible. Okay, let's look at some other applications of osmosis that are important. On the left here, we have a picture that shows the functioning of an artificial kidney. So one of the most important applications of dialysis is the use of this artificial kidney or kidney machines to purify blood. So what happens is the blood is passed through a cellophane tube which acts as a semi-permeable membrane. And that's what this pink thing is. This is the tube. And then the tube is put into a dialysizing solution, which is the background area here. The washing solution contains the same concentrations of ions and small molecules as blood, but has none of the waste products normally removed by the kidneys. The resulting dialysis, so movement of waste molecules out into the dialysizing solution, cleanses the blood. One thing that you might want to jot down is the word isotonic solution. I don't know if it's ever come up, but it's a good word to know. And they are solutions that have identical osmotic pressures. On the right here, another actual very good application, I guess, that we could use this for. This shows a desalination system that is actually set up on Cantina Island off the coast of Southern California. And this system can produce 132,000 gallons a day, which is a third of the island's daily needs. The salt water is pumped from underground wells into these 3 vats, and it goes through 20 micron and 5 micron filters at a pressure of 800 pounds per square inch, which is pretty strong. And then the fresh water is forced through additional filters and used, down here, the fresh water comes out here and then goes into the water supply for the island. The brine, which is like the salt and stuff, is pumped back into the ocean. I'm not going to cover reverse osmosis, but you might want to read about it. It's just really short. They haven't asked about it, but it's like 1 paragraph on page 511. It really explains this whole process of desalination in a little bit greater detail. I've never seen them ask it on the AP exam, though. Okay, let's talk about the expected and the observed values. I mentioned these earlier on. We look at NaCl, we expect the Van Hoff to be 2, observed is 1.9. MgCl2, it's 3, the observed is 2.7. So, why the discrepancies? Well, I said it earlier on one of the slides. It's because of ion pairing. At any given instant, a small percentage of the sodium chloride ions are paired. So there may be some that didn't dissociate at a given instant or not yet, and therefore counted as a single unit instead of 2, which is when you actually get the observed value, it's slightly lower. We see these discrepancies more in very concentrated solutions as opposed to dilute solutions. Okay, the last thing, and it's not really anything I can talk about, is colloids. You need to read pages 514 and 515 in the textbook, just to have some general information about colloids. And that's it for this section. The next lesson will begin chapter 12.